All right, so our last chapter we're going to do is chapter 11. Okay, we're going to start out by talking about sequences. Okay, so basically a sequence, it's just a list of numbers. Okay, that's all it is. It's a list of numbers, and those numbers are in a specific order. Okay, here's an example of a sequence. Okay, this particular sequence I've named sequence B. Okay, generally they name it with a lowercase letter. And the terms in the sequence are 1, 1/2, 1/3, 1/4, all the way up to the nth term in the sequence. Okay, as far as we know, this sequence doesn't have an end. Okay, it just keeps going. Some sequences are infinite. Some sequences are finite. Finite means it has a starting term, stopping term. You could count how many terms there are. Infinite means it goes on forever. Okay, and the way you kind of use this notation to figure out what term you're talking about, if you wanted to know the third term in sequence B, you'd write B and put a 3 as a subscript. Okay, B sub 3 would be 1/3. Okay, B sub 2 would be the second term in sequence B. So that way, if we're talking about multiple sequences at the same time, each one will have its own name using a letter, and then each term has its position in the sequence. Okay. Generally, we try to make it simple. Have the first term be B sub 1. Second term, okay, B sub 2. Some books you might see start with the 0th term. So the first one is represented by B sub 0. That kind of gets confusing. Okay, so we'll try to do it this way. Okay, so for a sequence to be uniquely determined, there's going to be a rule for finding the terms in it. Okay, and there's different kinds of rules we can use. Some rules, basically, if I wanted to know the 5,000th term in the sequence, there might be a formula you can plug into directly and find the 5,000th term. Other rules, they depend on the terms that come before it. Okay, we'll study a few sequences like that. So in other words, to find the third term, you have to do something to the one before it, the second term. But to find the second term, you have to do something to the one before that, the first term. Okay, we'll talk about what kind of formula is better. One where you have to know all the ones before the one you want, or a formula you can just plug into and find whichever term you want. Okay, so here's a sequence. This type of sequence is called arithmetic. Okay, we'll talk about what that means in a little bit. But I want to see if I can try to find a formula for it. When a sequence is arithmetic or geometric, there's a pattern you can follow to find the formula. This time, I just want people to look at it and see if they can figure it out. All right. So it's going to have a variable in it. The variable you're going to use is n. And you're going to do something to n to get the term. Sometimes it's helpful if either above or below, put what n is in each case. This is the first term, second term, third term, fourth term. See the pattern, Marina?
Well, each term you're adding 3.
Okay, so we are adding 3 each time. So that's one way we could look at it. Basically, you could say, we're going to add 3. What are you adding 3 to, though, to get the term you want?
To each previous term.
To the one right before it. Anybody have a guess how you'd write the term before a sub n? What would come before that? It's not going to be a number. It's going to have a variable in it. But, yeah.
Would it be, the whole thing just be 3 to the n minus, or no, 3 times n minus 1?
Let's hold off on that for a second.
Oh, okay.
But that's a good idea. But we kind of went this route, so let's finish this first, and then we'll talk about that.
A sub n minus 1?
Yeah. This is a perfectly acceptable way to write the formula for that sequence. Basically, it says to get the term you want, take the one before it, and add 3. All right, now Andrew, you were saying something else. What were you saying?
I was saying in parentheses 3 times n, and then minus 1.
That formula will also work. Okay, what Andrew's saying is, he's not saying take the one before it and add 3. He's saying whichever term you want, okay, if you want the third term, triple it, and then minus 1. If you want the fifth term, triple it, and then minus 1. Okay, let's see if it works. Let's check the fourth term. If you want the fourth term, triple 4 is 12, minus 1 is 11. Okay. These are two different ways of writing the formula. Which one do you think is more helpful? Yeah?
The 3n minus 1.
Yeah, how come?
Because you don't need a number before.
Right, you don't need anything before. If I wanted you to find the 300th term here, it's 899. Very simple. Just plug in 300, triple it, minus 1. Okay, using the formula above, if you want the 300th term, you'd take the 299th term, the one before it, and add 3. Okay, but to get the 299th term, you've got to take the one before it, the 298th term, and add 3. So you'd have to find every term before that to get the one you want. Okay, in general, some formulas are kind of hard to change from this type into that type. Okay, some are easy. This one was pretty easy. Okay, but some can be very, very difficult. Okay, so basically what we're going to come up with to describe these sequences are functions. We're looking at them as functions, but we're only plugging integers into the function. Okay? You can find the first term, the second term, third term, but there's nothing between the second and third term. So you wouldn't plug in like 2.4. Okay? So basically you can think of everything we're going to work with this week as functions. But the domain is just integers because it represents the term number you want. First term, second term, third term. So there's no such thing as the 2.3 or 2.3 term. Okay. Any questions on that idea? Okay, in finding patterns in numbers, that it can get very difficult. Okay, in general, we're not going to look at ones that are too challenging, but you could have simple patterns like the one we had. If you were to graph this bottom equation, that's basically a line with a slope of 3, y-intercept at -1. Okay, it's a linear pattern, very simple. Okay, we could get into ones that are quadratic, okay, or cubic or quartic, any polynomial pattern. But to do it by hand, we'll stick with ones that are straightforward. All right, so there's a couple different kinds of sequences, okay, infinite and finite. Okay, an infinite sequence would be defined by a function whose domain is the entire set of positive integers. Okay, we'll never look at plugging negative integers into a function because that would represent terms before your sequence started, which doesn't make sense. Okay, so an infinite sequence is defined by a function whose domain is the set of all positive integers, okay, with no end. Okay, a finite sequence, basically it has a start and it has an end. Okay, you could count how many terms there are in it, or you could add up all the terms and it would add up to a number. Okay? So the domain is a subset of positive integers from 1 through n, and it stops at whatever n is. Okay, so I made a reference here to a series. Okay, kind of just said it quickly. But I said you could add up all the numbers in a finite sequence, and it would add up to something. How about an infinite sequence? Do you think it's ever possible you could add up infinitely many numbers, and you actually get an answer? What do you think, Josh? No? Anyone think you can add up infinitely many numbers and you'll actually get an answer? A couple people think you can? Think back to that first sequence I had. Okay, this one. What happens if we're not adding these up, but if we were adding them up, what's happening to each term as you get further and further from the beginning? Well, Sam?
Gets smaller.
Yeah, it gets smaller and smaller and smaller. In fact, what does each term approach as the terms go further and further away from from 1?
0.
Yeah, approaches 0. All right, so eventually you're adding a number that's very, 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 very small. Okay, like 1 over 1,000, 1 over 1,000,000. And we'll talk about that when we look at a series. Okay. But it is true. You could add up infinitely many numbers. And because the numbers are just getting so small, it approaches a value. It doesn't reach the value, but it approaches it. You could kind of think of it like an asymptote, something getting very, very close. And of course, in a finite sequence, you can always add the numbers up because there's a fixed amount of terms to add. Okay, any questions on the difference between an infinite and a finite sequence? Okay, so for today, we're just listing a bunch of numbers with commas between them. We're not going to add up the numbers yet. Okay, so this is just practice trying to list out terms given a formula for a sequence. Okay, this one is it's written with a quadratic in the top, okay, and a degree 1 in the bottom. Okay, you could also write it like this. It's the same thing. This might be a harder pattern to come up with. Okay, so let's start with a sub 1. Okay, what would be the first term in that sequence? Fill in 1 for n. Just tell me what you get. 1? Well, let's double check. Plug it in the top. What's 1 squared?
0 over 1.
0 over 1, which is 0. Okay, so the first term in that sequence is 0. Okay, second term? Michael?
1.5.
Okay, and how'd you get that? I think you are correct, but how'd you get that?
I plugged 2 in for n.
Yeah, you plug 2 in for n. Because the numbers are going to kind of get messy, I'll leave it as a fraction. 2 squared is 4, minus 1 is 3, over 2, or 1.5. Okay, Orlando, what about my third term?
8 over 3.
Yeah, 8 over 3. So 3 squared is 9, minus 1 is 8, over 3. Okay, and then finally, let's go all the way to the 15th term. So plug in 15. 15 squared is 225, minus 1 is 224, over 15. Okay, if you need to, you can just type it in and check it. Okay, and notice to find the 15th term, we didn't have to know the 14th or the 13th or the 12th or the 11th. We found each one of those terms separately. Didn't have to find the one before it. In a couple cases we did, but we didn't have to. Those were just the directions. Okay, any questions on that? Okay, so that's just listing terms out, given a formula for the sequence. Okay, what do you think is going to happen here? You're going to get kind of a pattern here, like something switching back and forth. Yeah?
If it's an odd number, it's going to be negative, and if it's an even number, it's going to be positive.
Right. Okay, this is basically how you change from going positive, negative each time. All right? If you put in -1 to the end, all it's going to do on an odd power is make it negative. On an even power, it's going to cancel out. Okay, so let's try the same thing. We'll find the first 3 terms and then the 15th term. All right, Shannon, what's -1 to the 1?
-1.
Yep, negative 1. And then 2 to the 1, 2. Okay, so our first term is negative 2. Okay, second term, it's going to be negative 1 squared, which is 1. And then 2 to the second, which is 4. We get negative, positive 4. Okay, Tahina, how about my third term? Or walk me through it. How would I find the third term? Negative 1. Because you're going to raise it to the third power. You get negative 1. And then 2 to the third power is 8. So what does that come out to? Good, negative 8. Okay, so if you notice here, basically you have an exponential, right? 2 to the n. It's just an exponential curve. But what's happening is it's going positive, negative each time. Because if you tried to graph something like this, you'd get some weird results. And keep in mind, your calculator is going to try to plug in n real numbers. Okay, it's going to plug in like 1.2, 1.3, 1.4, things that wouldn't make sense in our pattern, in our sequence. Okay, and then lastly, the 15th term. Okay, we've already pointed out the pattern. Anything to an odd power. In this case, negative 1 to an odd power. It's negative 1 times 2 to the 15th. So 32,768. Okay, so that's a good trick to keep in mind. If you want a sequence to alternate positive, negative, just throw a negative 1 to the end. What if I wanted to change the positive, negative in terms of the first one being negative? Let's say I wanted it positive, negative, positive. How could I adjust my sequence to make that happen? So instead of negative, positive, negative, I want to just start on a positive instead.
Well, you could take, instead of raising it to just the nth power, you could raise it to the n plus 1 power.
Exactly. You could put a plus 1, you could put a minus 1. Either one would accomplish the same thing. Yep. And then it would change the order of the alternating positive, negative. Okay, very good. Okay, so we already said earlier, our sequence is basically a function. It's defined by a function. The only restriction is you're only allowed to plug in integers for the domain. 1, 2, 3. Nothing between 1 and 2. Okay. So let's try graphing a sequence. Okay, when we graph it, the idea is you're going to graph it just like you'd graph a function, but you're going to have dots. You're not going to connect them. And the dots are going to represent the terms. Okay, so this is a sequence we looked at a little bit earlier. Okay, so n, that's like your x column, and a sub n, that's what you get when you plug n into the formula. It's like your y column. So n's are like your inputs, a sub n is your output. Okay, we've already gone through what you get here. So you plug in 1, we get 0. Plug in 2, we get 3 halves. In this case, I think the decimal will be easier because we're going to graph it. Plug in 3, you're going to get 8 thirds. 2.7. And let's do one more. Plug in 4, you get 15 over 4. Okay, so graph those points and only those points. Don't connect them because there's nothing between these points. Okay. All right, so we've got the point. Bigger. 1, 0. 2, 1.5. And also, once you graph the points, you might start to get an idea if it's a linear pattern, or maybe it's curving up faster than that. Okay, 3 is 2.7. And 4 is 3.75. It's kind of hard to tell just graphing the first 4 terms. It almost looks like it's linear. But we're also maybe starting to get a hint that it's going to curve downward a little bit. So if you wanted to see, graph a point like 10. Okay, let's see what happens when we go all the way out to 10 and see, do we keep continuing up linear, or does it kind of curve and level off? So we plug in 10, you're going to get 10 squared is 100 minus 1 is 99. 99 divided by 10, 9.9. So it looks like it does just kind of keep continuing up. Any questions on graphing that sequence? If you have to graph it, all you got to graph is like 4 or 5 points. That's good enough. But don't connect them. Okay, don't connect them. All right, so all the formulas that we've been looking at so far, those are called explicit formulas. They allow you to directly find any term you want without finding anything that comes before it. Okay, that's called explicit. Definitely the best formula you can come up with for a sequence. Does anybody know what it's called when you have to find all the ones that come before it? It's an idea. It's used in computer programming a little bit. It's a way of, does anyone in here do any programming? A little bit? It's a type of programming if you've ever done like a Towers of Hanoi problem. Have you ever studied that? It's like a game kids play. You've got three posts. You've got rings on a post, and you've got to move all the rings from one post to another post, but you can never put a bigger ring on top of a smaller ring. So you have to move the rings, and there's a pattern to do it, and it's the name of what I'm about to show you. It's called. It's called recursion. Okay. Or the type of formula we're studying is a recursive formula. Recursion or recursive formulas, they can start to get kind of complicated, especially when you get into computer programming. It's almost like if you put 2 mirrors, you could see the reflections bouncing back and forth, and it almost looks like infinitely many times you see something being repeated in itself. With computer programming, there has to be an end. It has to stop somewhere. It can't keep going forever. But it is kind of complicated to do if you're not used to it. Okay, but the idea in a recursive formula, you've got to be given a little bit of stuff to start with. Okay, first term, maybe the first couple. And then the term you want is going to be defined by using the previous term, or maybe even previous terms before that. So here's an example of a very simple recursive sequence we've already seen today. This tells you that the first term in the sequence is 2. And then to get any term you want after that, take the term before the one you want and add 3 to it. So if I wanted the second term, just fill in 2 for n in that equation. So a sub 2 is 3 plus a sub 2 minus 1. 2 minus 1 is 1. And now you go back and you say, oh, I already know that term. Plug it in. And a sub 2 is 3 plus the one before it. The one before it was 2. So in this case, you get 5. Okay, if I wanted a sub 3, well, I'd fill 3 in. A sub 3 is equal to 3 plus a sub 3 minus 1. 3 minus 1 is 2. So now I need the second term. But I already have that. So I fill that in. And I get 8. Okay, so it all goes back to the very first term, and you're basically plugging it in all the way down your formulas to get the one you want. Okay, now that's a very, very simple recursive sequence. Okay, here's something that you could see, another example, a little more complicated. And this isn't even really that complicated. But this is basically saying to get the term you want, you go back to 2 terms before it. You take that term and you triple it. And then you go to the term just before it, you double it, and you add them together. It'd be very difficult, I think, looking at a sequence of numbers to come up with that formula by hand. And in general, if you're given a sequence, sometimes you don't know how many terms it depends on. Maybe the term you need just depends on the 1 before it. Maybe it depends on the 2 before it. Maybe it depends on the 10 terms before it. And every one could be a little different what you do. Okay, there is a process to turn something like this into an explicit formula. We're not going to study it. Okay, but you can. Okay, so this is kind of the same idea that we just did, except now we're going to do the recursive sequence. Okay, I'm going to start you off with the first term. I'm going to tell you how to get every term after the first term. So we'll write out the first 4 terms and the 8th term. Okay, Sylvia, what's my first term here? Yeah, 2. Okay, first term is given. Nothing you have to calculate there. Okay, Justin, how about my second term? Yeah. So you get the second term, take the 1 before it, add 4. Okay, Carly, my third term? 10. 10? And my 4th term, about Brian.
14.
Yep, 14. Now, if this was an explicit formula, we could just jump right to the 8th term. Okay? But because it's recursive, we have to go through and find the 5th, 6th, and 7th just to get to the 8th. So Orlando, can you give me the 5th, 6th, and 7th term?
18, 22, 26, and then 30.
Yeah, so then the actual one they wanted, the 8th term, was 30. What do you think, besides the time it takes, what's another disadvantage to finding the terms this way? Carly?
If you screw up on one, it'll mess you up for the entire sequence.
Yeah, once you make a mistake at one spot, okay, unless you make another mistake that undoes your first mistake, chances are you're going to be messed up for the whole sequence. Okay? So that's another downfall of recursion. Okay? Make one mistake, you're pretty much all done. Also, as I already said, but the time, if I asked you to find the 900th term this way, not the best way to do it. Does anybody see the explicit pattern? I was just looking at it quickly. Yeah?
You add 4 each term before it?
Well, that's the recursive pattern, adding something before it. But I'd like, let's say I said, tell me the 3,756 term. If you know the explicit sequence, you can do that with your calculator in under 3 seconds. You want to see the explicit pattern? Yeah?
Multiply it by 4 and then minus 2.
Yep, it's 4n minus 2. Multiply that by 4 and then subtract 2. Multiply by 4, subtract 2. Very good. How'd you figure that out? Did you do anything or like in your head, like a formula, or?
I just looked at 7 and 8 and then got it.
Just like that, yeah. Generally, arithmetic sequences, which this one is, and you're adding the same number, they're pretty easy to change from recursive to explicit. Not too bad. That's good. Okay, I'm going to have you guys try that right here. Okay, so I'm giving you a recursive formula. I want to change it to explicit. The easiest way to do that is to write out the first few terms in the sequence and see if you see a pattern. Okay, so I got my first term is 3. Brandon, what's my second term?
8.
Yep, 8. And Julia, my third term?
Oh no, I'm still like writing my
Right.
problems and trying to figure it out.
So our rule basically says whatever term you want to find, go to the one before it, and then add that much to it.
I'm 13.
Yeah, so we're going to get 13. So we can see we're adding 5 each time. And maybe that 5 has something to do with the explicit formula. Usually it does, yeah.
Times 5 minus 3.
Yeah, this one is times 5 minus 2. Okay, so the 5, that came from what we were adding each time. Where did the minus 2 come from? We'll look at that in a little bit. So it's times 5 minus 2. Any question on that formula? All right, so our next pattern, we're going to look at, some people have probably heard it before, Fibonacci sequence. Anyone ever heard of that one? Fibonacci? Okay, so the Fibonacci sequence, it's a famous sequence. Okay, it's defined recursively. You can also define it explicitly. It gets a little bit beyond what we do in pre-cal. It's actually a little challenging to do it that way. But the idea is you start with the first 2 terms. Okay? And define the next term. Take the 2 terms that come before it and add them together. So if you're given a recursive formula and it depends on the previous 2 terms, they got to start you off with 2 terms. If it depended on the previous 5 terms, they'd have to start you off with 5. Okay? So Cassie, what would my next term be here?
1 or 2.
All right. Well, let's look at it. We're going to find this first, second. We're finding the third term. What's 3 minus 1?
2.
Yep. So taking the second term. And 3 minus 2? 1. So to find the third term, take the second term and the first term and add them up. So we won't get 1, but we'll get 2. Okay, how about my fourth term? Michael?
3.
Good, 3. Okay, next term, Tahina? Not sure. Can you explain what that means to me? Kind of in your own words. without saying a sub n equals a sub n minus 1 plus a sub n minus 2, too mathy. Can you explain that to me, like maybe so like a second grader could understand it? Anyone help her out? Just explain that to me much, much simpler than all that math stuff. Yeah.
So the number that you're looking for in the sequence is basically, it's the number before it, just before it, so the previous number, added to the number that's two numbers before it.
Yeah. So the idea is just take the two previous terms and add them together. That's exactly what Marina just said. Take the two that come before the one you want and add them up. All right. So kind of going by that little bit simpler definition, what would the next term be, Tahina? 5, yeah. So we get 5. And how many do they want? The first 6? So we need one more. 8. Okay, and that's called the Fibonacci sequence. So notice each time you're not adding the same thing. So it's not an arithmetic sequence. And we'll leave it at that for defining it recursively. Okay. Take a look at an interesting pattern. Has anyone ever seen that before? This pyramid here? Or triangle? Let me make those numbers a little bigger so people can see them. Does anybody notice any patterns here? Besides, there's all ones going down the left, all ones going down the right. There's all kinds of interesting things that happen in this triangle. One thing I'm going to show you having to do with the Fibonacci sequence. Yeah?
So each number is the sum of the numbers above it to the left and to the right.
Yeah. If you take any number and you just look at the 2 above it, that's how you get that number. Like 3 plus 3 is 6, 3 plus 1 is 4, 1 plus 2 is 3. Okay. And there's a name for this triangle. Anybody know the name? Begins with a P. Not Pythagorean. Although that has a lot to do with triangles too. This is Pascal's triangle. Okay, Pascal's triangle. And what I've done is I've drawn some red lines on the diagonals. And I want you to watch what happens if I line it up just like that. Okay, so they go right through the middle of those hexagons. Okay, I want you to look at the top one. If you add up all the numbers that it goes right through, if it goes through a boundary between 2, don't count that. Just go add up the ones that it goes right through the middle of. For that first diagonal. Shannon, what do you get when you add up all the numbers that it goes through the middle of?
1.
You get 1. Okay. Now look at the next one. You get a 1 and a 1. That's a 2. Okay. On the next one, it goes through a 2 and a 1. Gives me 3. So far, this could be any pattern. Let's keep going. On the next one, you get, let's see, a 1, a 3, and a 1. Okay, if you add those up, you get 5. Let's do one more. We get 3, 4, 1. Gives me 8. What sequence of numbers is that? Yeah, that's the Fibonacci sequence. Okay. We didn't get the first one repeated unless I position it like that. Okay. If I positioned it like that, then you'd get a 1, and then another 1, and then the pattern from there. All right, so putting in those diagonals, you get Fibonacci numbers. Another thing that you can use this triangle for, we're going to use it a little later in chapter 12 when we talk about combinations and permutations. So like if I said to you, if I had 3 markers, what are all the different orders I could put them in? I've got green, red, black. I could have, red, black, green. What are all the different ways I could do it? This triangle can help you figure that out. Okay, specifically with combinations of things. Right? It has to do with how many ways you can order things. So there's a lot of different uses for this triangle. Probably a lot of things I don't even know. All right, so the last two things I'm going to mention, I've already been mentioning them throughout class. Two types of sequences, or you can also call it a progression. Okay, the first one is an arithmetic sequence. So a sequence is arithmetic if there's a number d such that this equation is true. Basically, it's a number that you add to the previous term each time to get the next term. D is the common difference of the sequence. So in other words, if you took two terms that were next to each other and subtracted them, you'd get the same answer every time. Here's an example of an arithmetic sequence. If I take two terms that are next to each other, like 11 and 8, subtract, I get 3. 14 minus 11, 3. 17 minus 14, 3. So if you're given something recursively that's arithmetic, we have a formula. We're not going to have to try to guess anymore. That will automatically change it to explicit. Okay, there's a couple things you have to know. First, you got to know the first term. Okay, next thing you have to know is D. Okay, what's the common difference? Or you could look at it as, what's the number you're adding each time? If you know those two things, you're all set. That's all you need to figure out the formula. Just remember that n has to be a positive integer. N can't be a fraction, can't be a decimal. It's a term number. It's a positive integer. Okay, and generally, we'll clean that up a little bit. Once we know D, we can distribute it out. And then once we know a sub 1, we can combine some like terms. Okay, so your explicit formula for an arithmetic sequence is the first term plus n minus 1 times the common difference. Okay, I'll keep that up while we look at our next problem. Okay, what's wrong with example 6, the way I've written it? Yeah?
We don't know the first term.
Right, if you don't know the first term, you can't do this. It says to take the term before it and add 3, but you don't have a starting term. Right, so I'm just going to make up a starting term different than 5, otherwise it's going to be the same problem I just wrote in green. So let's let the first term be 7. So really, using this trick right here, you don't even need to list out the terms. This formula kind of takes all the guesswork out of an explicit, finding an explicit formula for an arithmetic sequence. Right. All we need is the first term. Okay, now we've got it. And what's my common difference? Or what am I adding each time to get to the next term? Yeah? 3. Just fill in those two numbers in the formula and see what we get. So we get a sub n equals the first term plus n minus 1 times 3. Anything that you can distribute and simplify, go ahead and do that out. All right, so distribute out the 3. You get 3n minus 3. Okay, I'm going to put 3n first just because we usually write it in descending order. And then 7 minus 3 gives me 4. It's always a good idea just to check it, see if it works out. Take your term, triple it, and add 4, and see if that works. Okay, let's try it. Let me list the second term and the third term. Okay, so I just used the recursive formula to add 3 a couple times. Let's check it. Okay, if you want the second term, 3 times 2 is 6 plus 4. Yep, gives me 10. Third term, 3 times 3 is 9. 9 plus 4, 13. Yep, seems to work. Notice I said it seems to work. We didn't prove it worked. We can prove it works. Okay, we can actually do a proof. But we're going to save that for next week. Okay, there is a way to prove that there is no doubt this is the formula that works. Okay. Any questions on that? So this one says we've got the first 2 terms in an arithmetic sequence. Find the 5th term. Now the key they told you is arithmetic. If they just said, here's the first 2 terms of a sequence, find the 5th term. Well, there might be many, many ways to find the 5th term. But if there's arithmetic, there's only one. Okay, so let's find the 5th term, and then we'll see if we can come up with a formula. Okay, Taylor, what term comes next?
Positive 4.
Yeah, because it's arithmetic, that means you're adding the same thing each time, or subtracting. In this case, it's a plus 6 each time. So plus 6, plus 6, plus 6. Okay, not too bad to find the 5th term recursively. But if I asked you to find the 3,756th term, you wouldn't want to do plus 6 each time. Okay, you want to come up with a formula. And Nick, do you remember what my formula was? Explicitly?
No.
Anyone help him out? What's that? Go ahead, Josh.
an equals a sub 1 plus n minus 1 times d.
Yep. And can you fill in d and a sub 1 in my example?
-8.
Yep.
Time, or was it plus?
Plus, yep.
N minus 1 times 6.
Good. Times 6. Okay, so we're going to get -8 plus 6n minus 6. And then lastly, combine my terms. So it's 6n minus 14. Okay, now you can find any term you want just by multiplying it by 6 and subtracting 14. How would you do that one? It's not too bad because they give you terms that are pretty close. But imagine if I gave you like the 3rd term and the 10,000th term. Try to think more general. Since it's arithmetic, what's the first thing you want to try to figure out? Marina?
I'm trying to figure out what number it is that you're adding to get to each time.
Right, it's figure out what we're adding each time, and which, we could just guess or subtracting. Obviously we're going from 13 to 3, so maybe we're subtracting 1 each time, maybe 2 each time. It's probably not much more than that. But in general, let's look at where we're at, where we're going, and let's see how many steps we take to get there. Okay? So we're going from 13 to 3. Okay, that's a difference of 10. And that's between, what is it, a sub 3 and a sub 8. So there's a difference of 10. How many steps does it take to go from a sub 3 to a sub 8? Yeah.
5.
Yeah, you're going 10 units and you're doing it in 5 steps. So difference of 10. Try to think of it as like you're walking steps from a sub 3 to a sub 8. Okay. And the quick way to do that is take the term you're at, the 8th term, 3rd term, subtract those two numbers. That's how many steps apart they are. 5 steps. So if we have a difference of 10, and we're doing that in 5 steps, what are we adding or subtracting each time? If it's getting smaller, we're subtracting. If it's getting bigger, we're adding. Yeah, this time just take 10 divided by 5. Gives me 2. Since it's going down, we're subtracting 2. So this time, our common difference is negative 2. And now I can use that to figure out my first term. If I add 2, I get 15. Add 2, I get 17. Yeah, another way, if you didn't want to have to add 2, let's say you had to go back quite a few, just count how many steps you have to go back. 2 steps. And multiply by the opposite of your common, or multiply by your common difference. That's what you'd add. Just remember that you're adding it, not subtracting it in this case. Okay, any questions on how you'd write the formula from here? Just fill in D, fill in A sub 1. So our last one is a geometric progression. A little different than arithmetic. This time you're not going to add the same thing each time. You're going to multiply. You're going to multiply the previous term by the same number each time. Okay, so an example of a geometric sequence would be something like 2, 4, 8, 16, 32, 64. It's doubling each time. If your constant you're multiplying by is less than 1, it's going to get smaller each time. And the constant you multiply by can't be 1, because if you multiply each term by 1, it will never change. So really, in a geometric progression, you only have 2 choices of what number you're going to approach. Anybody tell me what 2 numbers could I approach? And it all depends on if your constant's bigger than 1 or less than 1.
So if your constant is bigger than 1, you're going to end up approaching infinity.
Yeah.
And if it's less than 1, you're going to end up approaching 0.
Right. Okay, so if you multiply by a number bigger than 1, your sequence grows infinitely large. If you multiply by a number less than 1, or between 0 and 1, your sequence will approach 0. Right, so this is how we could define it recursively. To get a term you want, take the one before it, multiply by r. This time, r isn't the common difference, it's the common ratio. It's kind of like the common difference, but we're dividing to find what it is. So it's a little different. Okay, so there's an example of a geometric sequence. And if you want to know the common ratio, take any term, and then take the one before it and divide them. 16 divided by 8, 2. 8 divided by 4, 2. 4 divided by 2, 2. Okay, so in this case, common ratio is 2. And here's the explicit formula for changing a geometric sequence that's recursive into a geometric sequence that's explicit. Okay, if we can, we always want to use explicit. And the explicit formula says to get your term, take the first term and multiply by r to the n minus 1. Let's try an example of a geometric sequence, see if we can find a formula for it. Okay, so two things I need to find are a sub 1 and r. What could I find using those two numbers, -6 and 12? Could take those two numbers, do something with them, and that'll give me one of my letters right away. Yeah?
You can find R.
Yeah, I can find r. Okay, what would be my fraction I would set up to find r? Josh?
12 over -6.
Yeah. Just take any term, divide by the one before it, and that tells you what you're multiplying by each time. Okay. Somewhat obvious here, you could probably figure it out. But when you have messy fractions or decimals, if you can't figure it out in your head, just take a term, divide by the one before it. Right? That should also help you to figure out what your first term is going to be. Instead of multiplying that number by -2, if you divide it by -2, it's going to bring you back the other way. Okay, so my first term is 3. All right, so Andrew, what would be my explicit formula for this sequence?
3 and minus 1. 3.
What other number do we have to have in there that we found?
Oh, the first one.
So which number? Just tell me, because I'm not sure exactly what you mean.
3.
Yeah, we've got the 3.
Yeah. So, oh, you mean R?
Yeah, the first, yeah, we found r, -2. So where does that go?
R after 3.
Yeah, it's going to go right after the a sub 1. So just put it right after that. It's multiplied. Anything else I need?
Yeah. N minus 1.
Yep, n minus 1 exponent on r. Let's try it on the third term, see if it works. 3 minus 1 is 2. -2 squared is 4. 4 times 3 is 12. Okay, any questions on that one? All right. So I think that's pretty good. That's kind of a quick introduction to sequences. Tomorrow we're going to take sequences one step further and start adding up all the numbers in a sequence and see if they add up to something. All right, so homework, it's on 589. Okay, 1 to 7, odd, 9 to 13, it's all odds. Okay, 14, 17 to 27, and 31.